Hello there, welcome to Just About Space. Tonight, we're not going to rush through the cosmos. We're going to let it breathe, stretch and unravel in its own slow time, the way the universe itself moves, almost imperceptibly, until eons have passed. You're here, listening, as the quiet clockwork of reality ticks on in the background. This isn't about what's happening now. This is about the far horizon, the ultimate horizon. We live in a universe that had a beginning, a burst of existence, a hot flood of energy and matter we call the Big Bang. That much science tells us with confidence. But endings are quieter, more elusive. They're not marked by a single explosion or collapse, but by gradual, almost imperceptible transformations that stretch across billions or trillions of years. There's no single curtain call for the cosmos, no grand applause, just the changing of a stage set so vast, no single observer could witness it all. In this journey, we're going to travel forward, far forward, past the lifetime of our planet, beyond the lifespan of our star, beyond even the era when galaxies still shine. We'll drift through theories that physicists have built, each one trying to answer the same question: what happens when the universe grows too old to sustain what we know? Some of these endings are cold and slow. The heatdeath, a fading into blackness as all stars burn out and all matter drifts apart. Some are violent. The bigrip, where the very fabric of space-time stretches faster than it can hold itself together. Others are cyclical. The big crunch, a reversal that could bring everything crashing back to a singularity. And then there are stranger possibilities. Vacuum decay, sudden phase shifts, endings that happen in an instant without warning. But here's the strange thing: to think about the universe's end is to think about our own, not just the fate of humanity, but the fate of time itself, of every atom that has ever been. The ending of the universe isn't something we will live to see, but in a way, it's something we're already part of. Every action, every photon of light, every transformation of energy is a small note in the symphony that will someday reach its final chord. So tonight, we'll move gently through these possibilities. We'll let them breathe, not as apocalyptic doom, but as vast, slow truths, the kind that take place whether or not anyone is there to watch. Settle in. This is the long story. The story of how everything, the stars, the galaxies, the fabric of reality itself, will eventually end. And it begins, as all endings do, with time. Before we talk about how the universe might end, we need to understand when each stage of its long decline will unfold. The ending of the cosmos is not a single event. It is a sequence, an unbroken chain of changes, each one lasting millions or billions of years. To walk through it is to stretch your mind far beyond the scale of human lifetimes, past even the age of our species, our planet, and our star. Let's begin where we are now, in the so-called stelliferous era, the age of stars. At roughly 13.8 billion years old, our universe is still quite young compared to its potential lifespan. Stars are still being born from clouds of gas, galaxies still spin in their gravitational dances, and black holes silently grow in the shadows. If you zoomed out to watch the whole thing from some impossible vantage point, it would look vibrant, flecks of light glittering in a great black ocean. But the seeds of the end are already sown. In about 5 billion years, our own sun will exhaust the hydrogen in its core. It will swell into a red giant, engulfing Mercury and Venus, and likely searing Earth into an uninhabitable wasteland. For us, this will be a final act. No more oceans, no more green landscapes. But for the universe, it will barely register as a footnote. Stars like the sun are not rare, and their deaths are routine. Fast forward further, in roughly 100 billion years, the cosmic expansion driven by dark energy will push most galaxies beyond the reach of our telescopes. The night sky will grow emptier, not because the stars are gone, but because their light will no longer be able to reach us. Civilizations in that future, if they exist, might never know about the Big Bang, because the evidence will have slipped away into darkness. Eventually, star formation will slow to a trickle, The great reservoirs of interstellar gas will be spent or locked away, leaving only the aging stars to burn through their remaining fuel. By the time we reach about 1 trillion years from now, there will be no new stars at all. The universe will drift into the degenerate era where the main inhabitants are cooling white dwarfs, faint brown dwarfs, neutron stars and black holes. It's a quiet time. No bursts of supernova light. No new galaxies forming. The cosmos will be a collection of faint embers, glowing weakly against an ever-darkening backdrop. And yet, it will still go on. White dwarfs, those tiny hot remnants of sun-like stars, will take quadrillions of years to cool completely into cold, black lumps of carbon and oxygen, so-called black dwarfs. Beyond that point, the universe's fate depends heavily on the nature of physics itself. If protons are truly stable, then matter could persist indefinitely, clumping around black holes and slowly radiating energy. If protons can decay, as some theories suggest, then even the atoms themselves will eventually disintegrate, leaving only a thin bath of radiation and subatomic particles. That process would take on the order of 10 circumflex 34 years, a number so large it's barely imaginable. Black holes will be the last titans to stand in this fading universe, but they too are not eternal. Through a process known as Hawking radiation, they will leak away their mass over unimaginable timescales. A small black hole might vanish in a fraction of a second. A supermassive one at the core of a galaxy could take 10 circumflex 100 years to evaporate completely. When the last black hole dies, there will be nothing left to anchor space in any meaningful way. And then, the long drift into the dark era. No stars, no planets, no atoms, just a thin, cold smear of photons, neutrinos, and whatever stable particles remain. The temperature of the universe will hover just above absolute zero. Space will continue to expand, but there will be nothing in it to expand with. That's one possible roadmap. Others change the final act entirely. The Big Rip tears apart all matter long before black holes could fade. The Big Crunch reverses the expansion and collapses the universe into a singularity. Vacuum decay erases everything in a fraction of a second without warning. But no matter which ending is correct, the journey there is always slow, patient, and absolute. The universe does not hurry toward its end. It strolls there in steps measured by forces and timescales far beyond our comprehension. And yet, every single thing that exists is part of that walk. We are living in one chapter of the cosmic timeline, but the final pages have already been written in the language of physics. If the universe has a most likely ending according to current physics, it is the heat death, also called the Big Freeze. It is not an explosion, nor a violent collapse. It is in a way the quietest possible ending, the gradual fading of all activity until nothing remains but cold, still emptiness. To understand it, you have to think about entropy, a word scientists use to describe disorder. In physics, entropy is not just messiness. It's a measure of how energy spreads out. In a closed system, entropy always increases over time. It's the reason your coffee cools down, why stars eventually burn out, why no machine is perfectly efficient. And on the grandest scale, the universe is the ultimate closed system. Right now, our universe is still rich in usable energy. Stars burn, galaxies collide, black holes swallow matter. There's still structure and difference, but the second law of thermodynamics says that over time, these differences will even out. Energy will spread uniformly. Temperature will balance everywhere. In the end, there will be no more potential to do anything. In the heat death scenario, we follow the long decline of usable energy. Stars consume their fuel and die. New stars form, but only for a while. Eventually, as the reservoirs of hydrogen are depleted, star formation halts entirely. The once luminous galaxies fade into darkness, leaving only remnants, white dwarfs, neutron stars, black holes scattered through the void. Quadrillions of years later, even those remnants cool and fade. White dwarfs become cold, inert black dwarfs. Neutron stars radiate their last traces of heat. Black holes dominate for a while, swallowing the last bits of stray matter, but they too are doomed. Hawking radiation, a faint quantum leakage of energy from their event horizons, ensures that even black holes lose mass over incomprehensibly long periods. A supermassive black hole, the kind that anchors a galaxy, might take 10 circumflex 100 years to vanish. Once the last black hole evaporates, the universe enters its final phase, a thin, uniform soup of low-energy photons, neutrinos, and perhaps a few other stable particles drifting through an ever-expanding space. The temperature of this cosmic background will approach absolute zero but never quite reach it. What makes this ending so unsettling is its permanence. In the heat death, there is no mechanism for the universe to restart. There's no collapse back into a new Big Bang, no cycle of rebirth. It is the ultimate equilibrium, and in equilibrium nothing happens. No stars can ignite, no structures can form. There are no observers, no events, no distinctions between one region of space and another. It's tempting to imagine this as a kind of cosmic graveyard, but even a graveyard has landmarks, headstones, boundaries. Heat death is emptier than that. It is like a canvas wiped completely blank, not even white, just without color or texture, without the possibility of change. From our human perspective, it feels impossibly distant. And it is. The timescales involved are so enormous that if you lived for 1 billion years, you'd still only see the faintest tick of the clock toward heat death. And yet, in a way, we can see the process already. Every photon of heat radiated away from a star, every particle drifting into intergalactic space, every bit of energy that spreads out instead of concentrating, all of it is part of the slow march toward this final stillness. There is a strange beauty in the heat death idea. It is the most natural end in a universe governed by entropy. It requires no exotic physics, no unlikely reversals. It is simply what happens when all the fuel is spent, all the differences are erased, and all that remains is time itself, stretching into nothing. And perhaps that's the most haunting part. It's not a dramatic finish, but a slow dissolving into forever. The universe will not die with a bang, but with a silence so deep that not even the concept of silence will survive. The heat death of the universe is a slow fade into stillness, but the bigrip is its impatient, violent cousin, where heat death lets the cosmos grow old gracefully. The bigrip yanks it apart while it's still full of light, stars, and galaxies. It is a scenario driven not by the quiet work of entropy, but by an unstoppable acceleration of expansion. If it happens, the universe will end not in trillions upon trillions of years, but in a mere fraction of that time. To understand why, we have to look at one of the most baffling discoveries in modern cosmology: dark energy. In the late 1990s, astronomers studying distant supernovae found that the universe's expansion was not slowing down, as most had expected. It was speeding up. Some unknown force or property of space itself was pushing everything apart faster and faster. This force was given a placeholder name: dark energy. The big rip is what happens if dark energy doesn't just keep expanding space at a constant rate, but grows stronger over time. Imagine space as a flexible sheet with galaxies embedded in it. Right now, the sheet is stretching gently but steadily, and the galaxies are being carried apart by this stretch. In the big rip scenario, that stretching accelerates, not gradually but exponentially, until even the strongest bonds in nature can't resist it. At first, this acceleration doesn't feel catastrophic. Galaxies drift farther apart, and the night sky becomes emptier over billions of years. But at a certain point, the acceleration reaches scales where it starts breaking apart gravitationally bound systems. Clusters of galaxies fly apart. Then, galaxies themselves are ripped into individual stars. This is where the timeline starts to get terrifyingly short. If the acceleration keeps increasing, it will eventually reach the scale of solar systems. Planets will drift away from their stars. Moons will abandon their orbits. And then, still faster, the tidal stretching will attack the very stars themselves, pulling them apart layer by layer. The Big Rip doesn't stop at astronomical scales. Once stars are gone, it turns its attention to smaller systems. Planets disintegrate, torn into dust and then into molecules. Molecules themselves are stretched and snapped into atoms. And in the final seconds, literally seconds before the end, even atoms are ripped apart into their component protons, neutrons, and electrons. It's difficult to imagine this without thinking of some massive cosmic explosion, but it's not an explosion in the traditional sense. There is no shockwave, no central blast. It is space itself expanding so violently that nothing can hold together. Distances grow so fast that light itself cannot keep up, and all causal contact between points is severed. In most Big Rip models, the final moments are staggeringly fast. You could live in a galaxy where things seemed quiet for billions of years, and then in the span of a single human lifetime, see the night sky change beyond recognition. Near the end, things accelerate to a nightmare pace. The last stars might die minutes before planets fly apart, atoms moments before they are erased. How soon could this happen? That depends entirely on the properties of dark energy. Right now, our best measurements suggest that dark energy behaves like a cosmological constant, steady over time. If that's true, the Big Rip is off the table, and we're safe from it. But if dark energy's strength increases, even slightly, then the rip becomes possible. In some hypothetical models, it could happen in as little as 20 billion years from now, shockingly soon on cosmic timescales. In others, the universe might coast for hundreds of billions of years before the tearing begins. What makes the Big Rip so different from heat death is that it erases everything, not just stars and galaxies, but the very building blocks of matter. There is no lingering dark era filled with cold particles. There is no chance for anything to survive in some quiet corner. The rip is absolute. There is also no warning sign that we could detect far in advance. The acceleration could be slow and harmless for billions of years, then suddenly ramp up in the last sliver of cosmic time. From the perspective of a civilization living near the end, the whole sequence, from galaxies drifting apart to atoms breaking, would feel like watching the universe dissolve in fast forward. In a strange way, the Big Rip is the most personal of all the endings. Heat death is so slow that it's abstract. The Big Crunch, which we'll get to later, at least allows a universe to collapse back into itself in one colossal finale. But the Big Rip happens everywhere at once. There is no safe distance, no center, and no edge. When it comes to you directly, to your planet, your molecules, your atoms. There's an eerie philosophical twist to this. In the Big Rip, even the concept of space becomes meaningless at the end. If every point in the universe is being pulled away from every other point faster than light, then distance itself stops existing in any practical sense. The geometry of reality unravels, and when it's over, there is nothing left. Not just nothing to see, but no framework in which seeing or place could exist. Some physicists see the Big Rip as unlikely given current evidence, but the truth is we don't fully understand dark energy. It could evolve over time, it could shift unpredictably. The same force that shapes the expansion of the universe could, in the far future, become its executioner. So if heat death is the slow fading of a candle, the Big Rip is the sudden snuffing of a flame by an invisible, all-encompassing wind. Not gradual, not merciful, but swift, final, and without exception. If the Big Rip imagines the universe being torn apart by unstoppable expansion, the Big Crunch imagines the exact opposite. A universe that stops expanding, turns around, and collapses in on itself. It's an ending that feels symmetrical, poetic even. The cosmos began with a single, unimaginably dense point in the Big Bang, and it could end by returning to one. To see how this would happen, we need to think about what controls the universe's expansion in the first place. Ever since the Big Bang, space itself has been stretching. At first, gravity from all the matter in the universe worked to slow that expansion. For a long time, cosmologists assumed that maybe one day gravity would win. that the expansion would stop, reverse, and everything would begin to fall inward. For a big crunch to occur, the total density of the universe, matter, dark matter, radiation, and any other forms of energy, would need to be high enough to counteract expansion. Imagine you toss a ball straight up. If you throw it too gently, it will stop and fall back. Throw it hard enough, and it escapes into space forever. The same logic applies to the universe. Too little matter, and it expands forever. Enough matter, and it falls back inward. In the Big Crunch scenario, the reversal begins subtly. Galaxies stop drifting farther apart. The expansion slows to a crawl, then halts. Then, slowly, they begin to approach each other again. At first, this might be barely noticeable on human timescales, perhaps only the faintest shift in the redshifts of distant galaxies. But over billions of years, the pull becomes more obvious. Clusters of galaxies would begin to merge on a massive scale. Galaxies themselves would collide more frequently, tearing apart their structures and triggering bursts of star formation as gas clouds slam together. For a while, the night sky might actually grow brighter as these starbursts flare into being, but this would be a last gasp of activity before the end. As the collapse accelerates, the cosmic microwave background, now faint and cold, would grow hotter again. The universe's overall temperature would rise as matter and radiation are compressed into a smaller and smaller volume. Eventually, every galaxy would merge into an enormous swirling mass. The distances between stars would shrink dramatically, and radiation levels would become extreme. In the final stages, the collapse would happen faster and faster. All remaining matter would be drawn together into an ever smaller space. Black holes, already massive, would consume everything nearby, growing to sizes far beyond anything in today's universe. These supermassive black holes would then merge into even larger ones, until in the final moments, the universe would effectively be one enormous black hole itself. But the Big Crunch doesn't necessarily stop there. The idea is that the collapse would end in a singularity, an infinitely dense point, just as the Big Bang began. Space and time themselves would be drawn into this final point, erasing all structure, all separations, all distinctions. This is where the possibility of a cosmic cycle comes in. Some theorists have proposed that the end of a Big Crunch might trigger another Big Bang. In this cyclic universe model, the cosmos endlessly expands and contracts. Like the beating of a cosmic heart, our universe would simply be one cycle in an eternal series, each beginning with a bang and ending with a crunch. It's an elegant idea, but there's a problem: the discovery of dark energy. Since the late 1990s, we've known that the universe's expansion is not slowing down, it's speeding up. If dark energy remains constant or grows stronger, it will overwhelm gravity forever, making a Big Crunch impossible. For a crunch to occur, dark energy would have to reverse sign or fade away entirely, allowing gravity to take over again. Still, physics leaves room for surprises. Dark energy is one of the least understood elements of our models. If it is not constant, if it evolves over time in a way we can't yet predict, it's conceivable that its repulsive effect could weaken, and gravity could resume control. From a philosophical perspective, the Big Crunch offers a certain comfort. Unlike heatdeath or the bigrip, which leave nothing but emptiness, the Big Crunch compresses everything into something, even if that something is an infinitely dense singularity. There is an almost narrative satisfaction to it. What began in fire ends in fire. The laws of physics that govern creation are also the ones that govern destruction. And in this model, they are the same act viewed from two directions in time. The final moments of the crunch would be utterly alien. Temperatures would soar to unimaginable levels, matter and energy indistinguishable from one another. The fabric of space-time would warp violently as it collapsed, and the very notion of before and after would lose meaning. For any hypothetical observer, assuming one could exist at all in such conditions, the last instant would be a blinding, all-consuming wall of energy, then nothing. Or perhaps, then everything again. If the universe is cyclic, the Big Crunch is not the end but the beginning of another expansion, Another set of galaxies, stars, and possibly even life. Maybe the physics of the singularity reboots the cosmos, setting off another big bang. And if that's true, then somewhere in the unfathomable future, another civilization might sit beneath alien stars wondering how it will all end. That's the strange paradox of the Big Crunch. It is both the most final and the most hopeful ending we can imagine. Of all the ways the universe might end, vacuum decay is the most unnerving, not because it is the most violent, but because it could happen at any time, without warning, and without any way to see it coming. It is an ending that does not give you billions or trillions of years to prepare. It gives you nothing at all. One moment, everything is as it has always been. The next, the laws of physics themselves are rewritten, and everything you know ceases to exist. To understand vacuum decay, you need to know about the idea of the vacuum state in quantum field theory. In everyday language, a vacuum is simply empty space, no air, no matter, no light. But in physics, a vacuum is defined by the lowest possible energy configuration that the fields of the universe can take. Think of the universe's vacuum as the ground floor of reality, the most stable arrangement of energy that can exist. Placed, that sips what we hope. There's a possibility that what we think of as the ground floor is not actually the lowest floor. We might be living in what's called a false vacuum, a state that is stable enough to persist for billions of years, but is not the true, absolute minimum energy state. In this metaphor, the universe is like a ball resting in a shallow dimple on a hillside. It seems stable, but if it gets a strong enough nudge, it could roll down into a much deeper valley. That deeper valley would be the true vacuum. The trouble is, if a transition from a false vacuum to a true vacuum happens, it changes everything. The values of the fundamental constants, the speed of light, the strength of gravity, the masses of particles could all be altered. Atoms, as we know them, might not be possible in the new vacuum. Chemistry might not work. The building blocks of matter might not even exist in any form recognizable to us. And here's the part that makes this scenario so chilling. The transition would happen in the form of a bubble of true vacuum that appears somewhere in the universe. This bubble would expand at nearly the speed of light, consuming everything in its path. Inside the bubble, the new laws of physics take hold. Outside the bubble, the old laws still apply, but only until the bubble reaches you. You would never see it coming. The leading edge of the bubble would arrive faster than any warning signal could travel. One instant, you'd be going about your life. The next, the particles that make you up would no longer be compatible with the structure of the universe, and you'd simply stop existing. Not burned, not torn apart, just erased, replaced by whatever reality the true vacuum allows. How likely is this to happen? That depends on the shape of the energy landscape of the Higgs field, the field responsible for giving particles their mass. In 2012, the Higgs boson was finally detected at the Large Hadron Collider, and its measured mass suggested something strange. Our universe might indeed be metastable. That is, the current vacuum state is not the deepest possible one. If that's true, vacuum decay is not just a theoretical curiosity, it's a legitimate possibility. However, possibility does not mean imminent danger. The timescales involved in quantum tunneling events like this can be staggeringly long, far, far longer than the current age of the universe. It could be that the false vacuum will persist for another 10 circumflex 100 years or more before a transition occurs. Or it could happen tomorrow. The equations don't offer a precise prediction. There's also the question of whether some high-energy event could trigger the transition, something like the collision of two black holes, or even, in science fiction scenarios, an experiment in a particle accelerator. Most physicists agree that natural processes in the universe are already far more energetic than anything humans could produce, and so if the vacuum has survived until now, it's likely safe from our own activities. Still, the thought lingers. If vacuum decay is possible, it's an ending that sidesteps all the long, slow fades of cosmic time. It doesn't wait for stars to die, for black holes to evaporate, or for space to grow cold. It doesn't even require the entire universe to want to end. It just requires one random fluctuation in one tiny patch of space, and the rest follows automatically. Philosophically, vacuum decay is a humbling reminder of how dependent we are on the stability of the laws of physics. We take it for granted that the constants of nature will be the same tomorrow as they were yesterday. We build our entire understanding of reality on that assumption. But in this scenario, that assumption is temporary. If there's any silver lining, and it's a strange one, it's that such an ending would be instant and painless. There's no suffering, no drawn-out collapse. In a way, it's the cleanest end possible. The curtain simply falls without the audience even realizing the play is over. For all we know, somewhere far away in the universe, such a bubble might already exist, racing toward us at the speed of light, or perhaps it will never form at all. That's the unsettling beauty of vacuum decay. It's the ultimate unknown, hidden in the very fabric of what we call empty space. If the big crunch is the universe collapsing into a singularity and staying there, the big bounce is that same collapse but followed by a rebound. It's an ending that refuses to be an ending. In this vision of reality, the death of our universe is just the birth of another, and this cycle may have been repeating forever, long before our particular chapter began. The big bounce is not a new idea. In fact, ancient philosophical traditions often imagined time as a circle rather than a line, everything repeating in endless cycles. Modern cosmology gives this concept a scientific frame, suggesting that the laws of physics might permit a universe to collapse and then expand again, with each cycle giving rise to new galaxies, stars, and possibly life. Let's start with how it works. In a big bounce scenario, our universe first follows a path much like the Big Crunch. Gravity eventually overcomes expansion, perhaps because dark energy weakens or reverses its sign. The expansion slows, stops, and turns inward. Galaxies draw closer, merge, and dissolve into giant black holes. The universe's temperature rises as everything compresses into a smaller and smaller volume. In a standard Big Crunch, this process ends in a singularity, an infinitely dense point where space and time themselves end. But in the Big Bounce model, something different happens. Instead of a singularity that marks the final stop, the collapse reaches a critical density where quantum gravity effects take over. These effects, still poorly understood, could prevent the formation of a true singularity. Instead, the universe bounces, reversing from contraction back into expansion. Think of a ball dropped from a height. Gravity pulls it down, accelerating it toward the ground. But when it hits, it compresses, stores energy, and then springs back up. The Big Bounce imagines the entire cosmos doing something similar, though the floor is not a solid surface but a regime of physics we do not yet fully understand, the realm where Einstein's general relativity and quantum mechanics must merge. If the bounce is perfectly symmetrical, the universe after the bounce could be a mirror of the one before it, running through the same history in reverse. But most versions of the theory imagine an asymmetrical bounce, meaning the new expansion would be different. New patterns of cosmic structure would form. Stars and galaxies would assemble in ways unlike our own. Perhaps the constants of nature would shift slightly, producing a new variety of physics. And here's where the idea becomes truly vast. The bounce could be part of an infinite series. Each universe is born from the collapse of the one before it, stretching outward, evolving, and then falling back to seed the next. In such a model, the question, what happened before the Big Bang, has an answer. Another universe, one that ended in a big crunch that became our Big Bang, and before that, another, and before that. You get the idea. There are different ways cosmologists imagine this happening. One version comes from loop quantum cosmology, a branch of physics that applies principles of loop quantum gravity to the universe as a whole. In this model, space itself is made of discrete loops or quanta, and when compressed beyond a certain limit, these loops create a repulsive force that prevents infinite collapse, triggering the bounce. Another approach comes from certain string theory models, where our universe is like a brain in higher dimensional space, and collisions between brains can trigger cycles of expansion and contraction. The Big Bounce is attractive in part because it avoids the problem of a beginning. A single Big Bang with no before is difficult to grasp. Where did it come from? How did time itself begin? A cyclic model sidesteps this by making time eternal in both directions. There is no absolute start. There is only the ongoing rhythm of universes being born, growing old, and giving birth again. But the model also raises deep questions. If each cycle is different, is there any memory from one universe to the next? Could information somehow survive the bounce? Most evidence suggests that whatever existed before would be erased or scrambled beyond recognition. That means our universe might have emerged from countless others, each with their own galaxies, histories, and perhaps intelligent beings, none of which we can ever know. From a human perspective, the Big Bounce offers an odd form of hope. Unlike heatdeath or the bigrip, it doesn't lead to permanent emptiness. There is renewal. The lights come back on. In fact, if the cycle is truly endless, there will be infinite opportunities for stars to shine, for planets to form, for life to arise. Somewhere in those cycles, beings like us, or nothing like us at all, might gaze up at alien skies and wonder how it all ends. Still, we have no proof that the Big Bounce is real. Our current observations show a universe that is accelerating outward, not slowing down toward collapse. Dark energy would have to change dramatically for a bounce to occur, and we don't yet know if that's possible. For now, the Big Bounce is a compelling idea in the realm where theory stretches far beyond what we can measure. And yet, if you step back, it's hard not to be drawn to its symmetry. A universe that ends with the same grand gesture it began with, only to rise again in a new form, is almost mythic in its elegance. It's the phoenix of cosmology, burning itself to ash only to be reborn in the same cosmic fire. Once the age of stars has ended and galaxies have gone dark, the most enduring structures in the cosmos will be black holes. In the far future, when the last red dwarf star flickers out and the great clouds of gas that once formed suns have long been exhausted, black holes will remain as the final rulers of the universe. Their reign will last longer than the lifetime of all the stars combined, and it will be a rule of silence, darkness, and gravitational dominance. To understand why they take center stage, we need to trace the transition from the Stelliferous era, our current age of star formation, to what physicists call the degenerate era. This is the period after all star formation has ceased. No new light is born. The only objects left shining are the fading remnants of earlier times. White dwarfs slowly cooling, neutron stars shedding their residual heat, and the occasional flare from matter falling into a black hole. As time marches on, gravity will slowly rearrange what remains. Stars and galaxies will drift, collide, and interact, until most are either swallowed by black holes or flung into intergalactic space. Over vast timescales, the interiors of galaxies will grow quieter, leaving their central supermassive black holes as the primary anchors of mass. These behemoths, millions or billions of times the mass of our sun, will consume anything that comes too close. Stars, gas clouds, rogue planets, and even other black holes. But they will not be alone. Throughout the universe, stellar mass black holes will also persist, the remnants of massive stars that exploded as supernova. Over trillions of years, these black holes will wander the cosmic darkness, occasionally capturing stray matter. In a sky without starlight, these events will be rare, but when they occur, they will be the brightest beacons in an otherwise unlit cosmos. Collisions between black holes will still happen during this era, though they will become increasingly uncommon as the universe expands. When two black holes merge, they release enormous bursts of gravitational waves, ripples in space-time that spread outward at the speed of light. In the black hole era, these gravitational waves may be among the last signals of activity that could, in principle, be detected anywhere. For an unimaginably long period, black holes will dominate the gravitational architecture of the cosmos, but even they are not eternal. Stephen Hawking's famous insight, Hawking radiation tells us that black holes very slowly lose mass by emitting tiny amounts of energy due to quantum effects at their event horizons. For small black holes, this evaporation happens relatively quickly on cosmic scales. Quickly might still mean billions of years. For the largest black holes, however, the process is so slow it defies ordinary comprehension. A stellar mass black hole might take 10 circumflex 67 years to fully evaporate, a number that already dwarfs the current age of the universe. But the true kings of longevity are the supermassive black holes, which could persist for up to 10 circumflex 100 years before they disappear. That's a 1 followed by 100 zeros, an amount of time so great that the concept of year becomes almost meaningless. During these eons, the universe will continue to expand, and the matter around black holes will become increasingly sparse. Eventually, the only interactions they have will be with the faint drizzle of radiation in the universe, and with each other, in the rare instances where gravity still draws them together across the expanding void. The death of a black hole is unlike the death of any other object. There's no explosion, no remnant left behind. As it evaporates, the black hole shrinks, growing hotter as it loses mass. In the final stages, the evaporation accelerates, releasing a burst of high-energy radiation before vanishing entirely. For a supermassive black hole, this final flare would be the last flash of light the universe would ever see. After the last black hole has evaporated, the universe will enter the dark era. There will be no more large-scale structures, no sources of light or heat, only a thin, cold haze of low-energy photons, neutrinos, and possibly some exotic stable particles drifting endlessly in an ever-expanding void. The reign of black holes will have ended, and with it, the last tangible structures in the cosmos will be gone. Philosophically, the era of black holes is a strange chapter in the universe's story. It is an age defined not by creation but by preservation, by the long, slow holding pattern of the last massive objects resisting the ultimate fade. For trillions upon trillions of years, these dark giants will sit at the center of whatever fragments of matter remain, the last monuments to a universe that was once full of light. And when their reign finally ends, the universe will not just be quiet, it will be empty in a way that is hard for us to truly imagine. A place without events, without change, without time as we understand it. The black holes will have been the final keepers of structure, and when they are gone, only the formless will remain. In our everyday world, many things seem impermanent. Stars burn out, mountains erode, even the hardest metals eventually corrode into dust. But on the smallest scale, we tend to think of certain particles as eternal. Electrons, photons, and protons, the basic building blocks of atoms, feel immutable, like the foundation stones of reality. If everything else can crumble, surely they are safe. But what if they aren't set? Proton decay is the idea that even the proton, the positively charged particle at the heart of every atom, has a finite lifespan. If this is true, then the universe's most fundamental structures are not forever. They will, given enough time, vanish. And if protons go, atoms go. And if atoms go, everything built from them, stars, planets, life, will dissolve into a haze of radiation. The proton is remarkably stable by any human standard. In our current best experiments, we have never observed a single proton decay. Measurements from enormous underground detectors like Japan's Super Kamiokande have set lower bounds on the proton's lifetime, at least 10 circumflex 34 years. That's a 1 followed by 34 zeros, over 100 trillion years. In comparison, the universe is only about 1.38 quad 10 circumflex 10 years old. So even if protons do decay, it's not something we could hope to witness directly. Still, many theories in particle physics predict it should happen. In particular, so-called grand unified theories GUTS, which aim to unify the electromagnetic, weak and strong nuclear forces into a single framework. often imply that protons are unstable over unimaginably long timescales. In these models, a proton can spontaneously transform into lighter particles, such as a positron and a neutral pion, through rare quantum processes. The pion would then quickly decay into gamma rays, while the positron would annihilate with an electron, producing more gamma rays. The consequences for the far future universe are profound. Imagine a cosmos billions of trillions of years after all stars have gone dark. The only things left are degenerate remnants, black dwarfs, neutron stars, and black holes. If protons are perfectly stable, these objects could persist indefinitely, slowly orbiting each other in an ever-expanding void. But if protons decay, the clock is ticking for all normal matter. A black dwarf, for example, the cold, inert corpse of a star, might seem permanent, but over spans of 10 circumflex 37 years or so, its protons would decay, and it would slowly disintegrate into a cloud of subatomic particles and photons. Neutron stars, whose cores are mostly neutrons bound by gravity, would follow a similar fate, since neutrons themselves are made of quarks bound together into baryons, which would also decay. The decay process would be slow on a local scale. A single proton might last for quadrillions of years before decaying, but with enough time, the number of surviving protons in any object would dwindle until nothing recognizable remained. The universe would transition from being populated by massive, stable remnants to being filled with a thin, cold mist of radiation and leptons, particles like electrons or neutrinos that, in many models, do not decay. This has a strange interplay with the era of black holes. Black holes themselves are not directly affected by proton decay. They are made from whatever matter they consume, but once inside, that matter is lost to the outside universe until Hawking radiation takes over. However, the fuel supply for black holes would dwindle. There would be no solid objects left to feed them, only radiation and the occasional exotic particle. If proton decay is real, the universe's timeline changes dramatically. Instead of a long, stable era of degenerate matter, you get a gradual fading of all normal matter, well before black holes themselves evaporate. It's a different kind of heat death, not one where things simply drift apart and cool, but one where the very bricks of reality crumble into dust. It's important to note that proton decay is not universally accepted as inevitable. Some theories predict it, others do not. Supersymmetric models, for example, offer different lifetimes for protons depending on the details of the symmetry breaking. And it's entirely possible that protons are truly stable, that they will never decay, and will persist until the last black hole evaporates. Our experiments have only told us that if they decay, they do so much more slowly than we can currently measure. If they do decay, though, it adds another layer of inevitability to the universe's fate. There would be no way to preserve matter, no clever engineering, no artificial structures that could resist it. Everything we see today, down to the smallest speck of dust, would eventually dissolve into pure energy and subatomic remnants. From a human perspective, proton decay is a concept that almost defies imagination. We think in timescales of seconds, years, maybe centuries. Even civilizations might last millennia at most. Proton decay operates on scales so vast that it stretches the definition of time itself. Yet physics, indifferent to human perception, deals in such spans without hesitation. And there's something oddly poetic in the idea. The proton, which has endured since the first microseconds after the Big Bang, which has carried the charge of stars and planets for billions of years, might one day simply vanish, quietly, without fanfare, leaving behind a universe just a little more empty than before. Earlier, we explored heat death, the long, slow drift of the universe toward a state of maximum entropy, where energy is spread so evenly that nothing more can happen. We also explored proton decay, the possibility that even the most stable building blocks of matter are not eternal. When you put these two ideas together, you get a version of the universe's end that is both inevitable and absolute. In the standard heat-death scenario, the universe still contains matter, black dwarfs, neutron stars and black holes drift in the cold darkness for trillions or quadrillions of years. Even after the last black hole evaporates, there could still be stable particles left floating in the void. If protons never decay, those particles could persist forever. The universe might be lifeless, but not truly empty. But if proton decay is real, that last refuge of matter disappears. Heat death with proton decay means that not only does usable energy run out, but the atoms themselves are erased. It is the same endgame of complete thermodynamic equilibrium, but with the added certainty that nothing structured remains. Let's trace the timeline. We begin much as before the Stelliferous era. Our current age ends when the last stars burn out. Star formation ceases as the gas reservoirs in galaxies are depleted. Over the next trillions of years, white dwarfs cool into black dwarfs, neutron stars fade, and the only flashes of light come from rare collisions or matter falling into black holes. Now enter proton decay. Over unimaginably long spans, perhaps 10 circumflex 34 years or more, protons in these dark remnants begin to break apart. In any given moment, the odds of a particular proton decaying are almost zero, but over timescales that dwarf the current age of the universe, every proton eventually succumbs. The decay process is subtle at first. A black dwarf the size of Earth loses only a tiny fraction of its mass over quadrillions of years. But the decay never stops, and each time a proton disappears, it emits lighter particles such as positrons and neutrinos, and high-energy photons. These photons too eventually spread out into the thinning fabric of space, contributing to the universal radiation bath. Neutron stars fare no better. Neutrons are made of quarks bound into baryons, and if baryons are unstable, they also decay. Gravity might slow the process slightly in such dense objects, but it cannot prevent it. Even the densest neutron star will eventually dissolve into radiation and lighter particles. Black holes remain the final holdouts, unaffected directly by proton decay since their mass is locked behind an event horizon, but they will lose mass through Hawking radiation. And in a proton decay universe, they will find almost nothing left to feed on. As the universe empties, black holes starve, slowly evaporating over time scales up to 10 circumflex 100 years. When the last black hole dies, that's the end of anything that could be called structure. At that point, the universe is not just a cold void, it's a perfectly uniform sea of low-energy photons, neutrinos, and possibly electrons or other stable elementary particles, if any remain at all. The temperature is a hair above absolute zero. There are no clumps, no stars, no planets, no black holes, and no atoms. Every proton that ever existed has been erased from the cosmic record. What's fascinating and unsettling about heat death with proton decay is that it removes any possibility of revival. In a universe without proton decay, at least some matter survives forever. Theoretically, with infinite time, quantum fluctuations could spontaneously create new matter, or even whole new universes. But if the building blocks themselves are unstable, then nothing that relies on them can last long enough to seed a new structure. The philosophical implications are stark. This version of the end is not just about entropy winning, it's about the annihilation of the very ingredients of reality. It means that permanence is an illusion. Everything we see, from galaxies to grains of sand, is made of particles that are living on borrowed time. Even the proton, which has survived unscathed since the first millionth of a second after the Big Bang, has an expiration date. Yet, there is also a kind of strange elegance to this ending. It's clean. It's complete. There is no lingering debris, no frozen monuments to a brighter past, just a smooth, unchanging expanse, the universe's final featureless form. In this vision, the heat death is not merely a cooling of the fire, but a complete dissolving of the ash. Matter itself is a temporary arrangement, and when it is gone, the cosmos will be nothing but the faint hum of radiation and the endless silence of space-time. Most of the end of the universe scenarios we've explored so far imagine a single cosmic stage, one universe expanding or collapsing, cooling or tearing apart, until there is nothing left to see. But what if our universe is not the whole stage at all? What if it's just one bubble in an infinite froth, and its end is more like one small candle going out in a room already filled with countless others? This is the premise behind eternal inflation, a theory that takes the idea of cosmic inflation, the rapid expansion that happened fractions of a second after the Big Bang, and extends it indefinitely. In the standard Big Bang model, inflation is a brief event. Space swells exponentially for a tiny sliver of time, then slows, allowing particles, atoms, stars, and galaxies to form. In eternal inflation, that expansion never completely stops. It slows in some regions, like ours, where normal cosmic evolution can happen, but elsewhere, it continues forever, endlessly spawning new pocket universes. Picture boiling water. Bubbles form, grow, and separate, each one a distinct environment. In eternal inflation, the fabric of space-time is like that pot of water, except the boiling never stops. Our observable universe is just one bubble among potentially infinite others, each isolated from the rest by ever-expanding space. This framework changes how we think about the end of our universe. In a single universe model, the final fate, whether heatdeath, bigrip, or big crunch, is the end of everything. In an eternal inflation model, the end of our universe is just a local event. The larger multiverse continues without pause, spawning new universes even as ours fades away. In fact, in some versions of eternal inflation, universes can have different physical constants, laws, or even numbers of dimensions. The conditions inside each bubble are determined by the physics that takes hold as it cools from the inflationary expansion. That means the multiverse could contain bubbles where chemistry as we know it is impossible, or where time behaves differently, or where no matter at all can exist. From the perspective of an inhabitant inside one of these bubbles like us, it's impossible to directly see beyond the boundaries. The space between bubbles expands faster than light can travel, so no signal from another universe can reach us. But the theory predicts that inflationary expansion is so rapid and persistent that even as one region ends in a collapse or decay, countless others are still being born elsewhere. So, how does eternal inflation tie into the fate of our bubble? In this model, our universe can still meet any of the endings we've discussed. Heatdeath, big rip, big crunch, vacuum decay, but those are all just local events within the bubble. The inflationary space outside our bubble carries on regardless. New bubbles form, and the multiverse never truly dies as a whole. In fact, it's possible, though deeply speculative, that the end of our universe could itself trigger the birth of a new one. In some inflationary models, the collapse of a bubble or the conditions inside it near its end could create the seeds for another burst of inflation, birthing a daughter universe. In that sense, endings and beginnings are not separate events but different sides of the same process. The timescales in eternal inflation are as staggering as they are irrelevant to human experience. Our universe might last trillions of years before reaching its end. During that span, inflation elsewhere would produce an unimaginable number of other universes. Even if we vanish completely, the multiverse's population would keep growing. One unsettling implication of eternal inflation is that, statistically, our universe might not be special at all. If there are infinite universes, then anything that can happen according to the laws of physics will happen somewhere, infinitely many times. That means there could be other universes with planets like Earth, civilizations like ours, and even versions of you reading these same words, although separated from you by distances no traveler or signal could ever cross. For our own cosmic fate, this means that end becomes a relative term. Yes, our bubble will eventually run out of energy or collapse, but in the grander picture, the multiverse doesn't notice. It's like a wave dissolving on a beach. while the tide continues its endless motion. There is no final curtain, just the ongoing creation and destruction of universes forever. The philosophical shift here is profound. Most end-of-universe scenarios have a note of finality to them, a sense of everything closing down for good. Eternal inflation replaces that with an endless churn. Death is local, birth is constant, and the totality of existence, if totality even means anything in this context, is never still. Still, there's an irony here. Even if the multiverse lives on forever, we in our bubble will never see it. To us, the observable universe will grow emptier over time. Stars will fade, galaxies will vanish over the horizon, and eventually, whatever fate our bubble is heading toward will arrive. We will go into the dark not knowing how much is still happening beyond our reach. And maybe that's the strangest ending of all. An ending that is only an ending to us, but in the bigger picture is nothing more than the faintest ripple in an infinite sea. The cyclic universe is already a grand concept, an endless series of expansions and contractions, each universe dying in a collapse and then being reborn in another big bang. The multiverse is even grander, a boundless collection of universes, each potentially with its own laws of physics, born from the infinite churn of eternal inflation. But what happens when you put those two ideas together? You get something that is almost dizzying in scale, the cyclic multiverse. In this model, each universe is not a single one-off bubble floating forever, or fading into stillness. Instead, every bubble universe goes through its own internal cycles of death and rebirth. When a bubble's expansion eventually halts, whether through changes in dark energy, gravitational dominance, or some unknown mechanism, it contracts into a big crunch. That big crunch does not signal the end of the bubble's story. It triggers a bounce, a new big bang, and the start of another cosmic era. The key is that these cycles happen independently in each bubble. While one universe is nearing the end of its 40th cycle, another could be in the early days of its second. Some bubbles might go through only a few cycles before expanding forever and never bouncing again. Others might have been cycling for an eternity already. The multiverse becomes not just a static collection of bubbles, but a living, ever-changing field where each bubble has its own heartbeat. One way to picture this is to imagine an infinite forest, where each tree is a universe. Eternal inflation is the process that allows new trees to sprout forever. The cyclic aspect is what happens inside the tree, rings of growth and dormancy, each cycle leaving traces of what came before, even if those traces are blurred beyond recognition. From a physics standpoint, the cyclic multiverse requires that the laws inside each universe allow for a bounce. This could happen through mechanisms proposed in loop quantum cosmology, where quantum effects prevent a singularity and cause a rebound. It could also happen in certain string theory scenarios, where our universe is a 3D brain floating in higher dimensional space, colliding with other brains in a repeating cycle. Each collision is a big bang. Each retreat is the dark, cooling end of an era. If this is the reality we live in, then our own universe's fate is more nuanced than a single path to nothingness. Yes, we might be heading toward heat death, or even a big crunch in this cycle, but that doesn't mean forever. Instead, our universe could one day collapse back into a high-density state, only for a new expansion to ignite. That expansion might have similar physics to ours or not. And this is where the multiverse aspect makes things even stranger. In a single cyclic universe model, each new cycle might carry forward some memory of the last, perhaps in subtle imprints in the cosmic microwave background. In a cyclic multiverse, there is no single chain of cycles. There are countless chains, branching and running alongside one another. Even if our own sequence is destroyed or transformed beyond recognition, infinite other sequences continue, each with its own possibilities. One particularly wild implication is that universes could change type from cycle to cycle. In one cycle, the constants of nature might allow for galaxies and stars much like ours. In the next, slight variations could make a sterile universe where no structures form at all. In some cycles, life could flourish. In others, matter itself might not exist in any familiar form. The cyclic multiverse becomes a vast, unfolding experiment, one in which every combination of cosmic conditions is eventually tried. And here's the thing, from the inside you'd never know for certain which type of universe you were in. The transition from one cycle to the next could wipe out all traces of what came before. Every time, civilizations would rise with no memory of earlier runs, convinced theirs was the first and only. The truth, if this model is correct, would be that they are living in just one heartbeat of an infinite organism. In terms of endings, this changes the story profoundly. For us, the end of the universe might still mean the extinction of all life and the erasure of every structure we know. But on a larger scale, it's not an ending at all. It's the equivalent of a season changing, one phase in an eternal cycle. While our cycle closes, another opens, and beyond our bubble, other universes are moving through their own rhythms, some beginning, some ending, some mid-story. The cyclic multiverse also softens some of the philosophical sting of more final endings like heat-death. If our cycle truly ends in maximum entropy, that's only a temporary state before gravity or quantum effects or some higher dimensional dynamic triggers the rebound. In that sense, even the bleakest chapter is just a bridge to the next. Still, this model doesn't guarantee continuity in the way we might wish for. Even if there are infinite rebirths, that doesn't mean our particular history, our particular stars and planets, will ever come back. In fact, the odds are vanishingly small that any given cycle would repeat exactly. The comfort here is not in personal or cultural survival, but in the idea that the cosmos never truly runs out of stories to tell. And perhaps that's the real gift of the cyclic multiverse idea. It replaces the question, when does it all end, with what comes next. It invites us to see our universe not as a solitary doomed object, but as part of a much larger, more vibrant whole, one where every ending is a beginning somewhere else, and where the multiverse itself has no final page. In nearly every modern discussion of the universe's fate, dark energy plays the starring role. It's the mysterious force, or property of space, that's making the expansion of the universe accelerate instead of slow down. Ever since its discovery in the late 1990s, dark energy has been treated in most models as constant, a fixed, unchanging push that will continue forever. But what if that assumption is wrong? What if dark energy itself has a life cycle, and we are living in its peak age? What if, slowly but surely, it fades away? The idea of a slow death of dark energy changes the endgame in surprising ways. Right now, dark energy is thought to make up about 68% of the total energy density of the universe, with dark matter at around 27% and normal matter only 5%. This balance dictates the overall behavior of cosmic expansion. If dark energy stays constant, the universe will keep accelerating forever, leading to a far-flung future where galaxies vanish beyond our observable horizon, and a heat death follows. But if dark energy decays over time, even extremely slowly, the acceleration could weaken, halt, and eventually reverse. To see how, imagine the expansion of the universe as a race between two forces, the outward push of dark energy and the inward pull of gravity. At present, dark energy is winning. Galaxies that aren't gravitationally bound to each other are moving apart faster every day. But if dark energy's strength diminishes, the race changes. Gravity's pull doesn't fade in the same way. Over billions or trillions of years, if dark energy weakens enough, gravity could begin to slow the expansion, eventually stopping it entirely. The result? The universe might avoid a heat death or bigrip entirely. Instead, it could transition into a slower, more balanced expansion, or even reverse into a contraction. That contraction could eventually lead to a big crunch or a big bounce, depending on the physics at high densities. The mechanics of a fading dark energy depend heavily on what it actually is. In the simplest model, dark energy is the cosmological constant, a fixed property of space-time itself. But there are other models where dark energy comes from a dynamic field, often called quintessence. In these models, dark energy is more like a fluid that evolves over time, changing in strength as the universe expands. If this field slowly rolls toward a stable minimum, the amount of dark energy it produces could gradually drop to zero. What would we see if this were happening? Not much, at least, not in any short-term human sense. The change would be imperceptibly slow, noticeable only when comparing the universe's expansion over billions of years. Galaxies would still drift away from us for a long time. The cosmic horizon, the maximum distance from which we can receive light, would still shrink. But deep into the future, the pace of separation would slow. Farther still, galaxies might begin creeping back toward one another. The slow death of dark energy is in some ways a hopeful scenario compared to the bleak finality of heat death. It opens the door for a more dynamic long-term future. Instead of fading into a frozen darkness, the universe might recycle itself. Old galaxies could merge into vast new structures. Star formation could resume in compressed regions of gas and dust. Over eons, the cosmic web might reconnect, giving rise to entirely new epochs of light and activity. However, it's also possible for dark energy to decay without triggering a bounce. If it fades to zero, but the universe is already expanding too quickly for gravity to pull it back, we could still end up in a forever expanding cosmos. The difference would be that the expansion would slow down and asymptotically approach a constant speed, rather than accelerating forever. In that case, the long-term fate might still resemble a gentler form of heat death. Cold, quiet, but without the runaway acceleration of a bigrip scenario. There's another intriguing possibility. Dark energy could decay into some other form of energy or matter. In certain theoretical models, the field responsible for dark energy could transfer its energy into particles, flooding the universe with a new kind of radiation or matter. This could dramatically alter the cosmic landscape in ways we can't yet predict, potentially even triggering new physics events that reshape the entire fabric of space-time. One reason the slow death hypothesis is taken seriously is that we don't actually know why the amount of dark energy we observe is what it is. Its value is incredibly small compared to the scales predicted by quantum field theory, and there's no clear reason it should remain constant forever. If it is dynamic, then we might just be living in a temporary phase where it's dominant, a brief flash in a much longer cosmic history. In a philosophical sense, the slow death of dark energy adds another layer of impermanence to the universe. We already accept that stars, galaxies, and planets are temporary. This scenario says that even the rules of the large-scale universe, the balance between expansion and gravity, are temporary too. The stage itself is changing, not just the actors. And in the context of ultimate endings, this is a reminder that predictions are only as fixed as the constants we assume. If dark energy fades, the grand finale may look nothing like the one we currently imagine. The universe could end in fire, a collapse, in rebirth, a bounce, or in a long twilight, a slowed expansion, all depending on how or if dark energy dies. In the far future, trillions or quadrillions of years from now, if there are still observers of any kind, they might look up at the sky and notice something extraordinary, galaxies that once seemed forever out of reach beginning to drift closer again. For them, that would not be the end of everything. It would be the beginning of a new cosmic chapter. The discovery of dark energy at the end of the 20th century radically changed how we thought about the universe's fate. Instead of slowing down under the pull of gravity, the expansion of the universe was accelerating. The simplest explanation, a cosmological constant, made it seem that acceleration would continue forever, leading to heat death, or perhaps a big rip. But there's a stranger, more dramatic possibility. What if dark energy is not a constant at all, and not even destined to fade away slowly as we discussed in the last section? What if, at some point in the far future, dark energy reverses its sign? That is, instead of pushing the universe apart, it becomes a force that pulls it together, not unlike an anti-gravity engine suddenly flipping into a cosmic brake. This would be one of the most violent shifts imaginable in the large-scale behavior of the cosmos. In one era, galaxies would still be drifting apart, the night sky growing dimmer as their light slips beyond our reach. Then, imperceptibly at first, the outward acceleration would weaken. Eventually it would halt, and then, without any visible explosion or shattering, the universe would begin to contract. The reversal could happen for many reasons in theoretical physics. If dark energy is not a constant, but instead the effect of a dynamic field, such as the hypothetical quintessence field, then its energy density and even its pressure could change over time. In these models, the sign of dark energy's pressure determines whether the universe accelerates or decelerates. A reversal in sign would flip the universe from acceleration to deceleration and eventually into collapse. Some versions of string theory and scalar field cosmology allow for even more exotic behaviors. The field responsible for dark energy could be rolling in a potential well, like a marble in a bowl. As it rolls, its energy changes. If it moves into a region of negative potential energy, the overall effect on the universe's expansion could shift from repulsive to attractive. This is where the Big Crunch trigger lies. The timeline after reversal would unfold slowly at first. Galaxies that have been receding for trillions of years would begin to approach each other again. Large-scale structures, galaxy clusters, filaments, voids would start to shrink. Stars and gas clouds, which in an ever-expanding universe might have drifted into isolation, would instead fall back into denser regions. Over billions of years, the process would accelerate. As contraction continued, the cosmic background radiation, now cooled to near absolute zero, would heat back up. Matter would be compressed into a smaller and smaller volume, and galaxy mergers would become frequent again, triggering bursts of star formation as colliding clouds of gas ignite new suns. It would be, paradoxically, a brief era of renewed light in the universe's middle age. But the renewal would be short-lived. As contraction speeds up, gravitational interactions grow violent. Galaxies and black holes merge in massive, chaotic events. Temperatures soar across the cosmos as radiation is trapped in a shrinking volume of space. Eventually, all matter and radiation would be concentrated into an ever smaller region. In the last stages, the universe might resemble its earliest moments, a hot, dense, high-energy plasma filling all of space. The closer we approach the final singularity, the more extreme the conditions become. Stars and planets would have long since been destroyed. Even atoms could not survive the crushing density and rising temperature. The end would come when the scale factor of the universe, the measure of its size, shrinks to zero. In classical general relativity, this is a singularity, a point of infinite density where the known laws of physics break down. Space-time itself would end. But some theories suggest that this end could actually be a beginning. If the collapse reaches a point where quantum gravity effects become dominant, they might prevent a true singularity and cause the universe to bounce, triggering a new Big Bang. In that case, the reversal of dark energy would be the first step in a grand cycle, linking our universe's expansion to the birth of another. Of course, for a dark energy reversal to happen, its nature must be very different from what most current observations suggest. The latest data indicate that dark energy behaves very much like a cosmological constant, steady, unchanging, but the precision of these measurements is limited. A small variation in its behavior could, over billions of years, add up to a complete change of fate. Philosophically, the idea of a reversal is compelling because it makes the universe's story symmetrical, a beginning in a bang, an end in a crunch. It also reminds us that the so-called constants of physics may not be constant forever. Even the large-scale trajectory of space-time is subject to change. If this scenario is real, then no matter how long the expansion lasts, the universe will eventually turn inward. All the great structures of the cosmos will return to the same point they came from, and somewhere in that final instant, in the furnace of infinite compression, the seeds of the next universe may be sown. Most discussions of dark energy start with the assumption that its effects are constant, Even if it grows slightly weaker or stronger over vast spans of time, the change is usually imagined as slow and manageable. But there's a far more extreme possibility, and it makes the already alarming Big Rip look like a gentle rehearsal. This is the phantom energy doom scenario, a future in which the strength of dark energy doesn't just increase, it grows without limit. The repulsion accelerates faster and faster, overpowering every force in nature until not just galaxies and atoms are torn apart, but the very fabric of space-time itself is destroyed in a final catastrophic instant. To understand why this is so dangerous, we have to talk about something called the equation of state parameter for dark energy, denoted as www. If W equal ruse 1 W equals sign minus equal ruse 1 W equals sign dark energy, acts like the cosmological constant, steady and unchanging. If W when Drux 1 Drux 1, strange things happen. Phantom energy density actually increases as the universe expands. Normally, as space grows, the density of matter and radiation drops because it's spread over a larger volume. Even the cosmological constant remains, well, constant. But phantom energy works in reverse. The more space you have, the more phantom energy appears, which makes space expand even faster, which creates even more phantom energy. It's a runaway process with no natural braking mechanism. At first, the consequences resemble a more aggressive version of the Big Rip. The expansion rate rises. Distant galaxies accelerate away from us at ever greater speeds. The observable universe shrinks as more and more galaxies disappear beyond the cosmic horizon. But the crucial difference is the timescale. In a normal Big Rip scenario with modest phantom energy, it might take tens of billions of years for the universe to be torn apart. With strong phantom energy, the interval between everything's fine and everything's over can shrink dramatically to millions, thousands, or even mere hundreds of years, depending on the exact value of www. The sequence of destruction follows a horrifyingly orderly pattern. First, galaxy clusters lose their gravitational binding. Galaxies themselves are pulled apart next, their stars drifting away into the growing void. Then solar systems disintegrate. Planets flung away from their stars, moons from planets. Stars themselves are shredded as their outer layers are stripped away. But phantom energy doesn't stop there. The repulsive force keeps increasing until it reaches the scale of planets, breaking them into rubble and then tearing the rubble into dust. Molecules are pulled apart into atoms. Atoms are ripped into nuclei and electrons. Protons and neutrons are torn into their constituent quarks and gluons. And then, in the final, unthinkably brief moment, even those fundamental particles are separated from the space-time they inhabit, as the geometry of space itself becomes undefined. In the last fractions of a second, space-time ceases to be a meaningful concept. The coordinates that once defined distances and durations no longer exist because there is no coherent structure to measure against. Physics as we understand it stops applying, not because the rules have changed, but because there is no longer a stage for them to operate on. Some phantom energy models go even further, predicting that the destruction of space-time could trigger a kind of reheating effect, releasing the accumulated energy of the universe in a final burst. This could, in theory, seed a brand new expansion, a new universe emerging from the ashes of the old. But unlike the gentler cyclic multiverse scenarios, this would be a violent and unpredictable birth, with no guarantee of producing conditions anything like the ones we know. One of the strangest features of phantom energy doom is that, in principle, it can happen surprisingly soon in cosmic terms. If the value of www is far enough below -1, the end could arrive in tens of millions of years. far too short for the comforting "we have trillions of years" narrative of other scenarios. Our current observations of dark energy suggest WWW is very close to -1, but the uncertainties in measurement leave room for a phantom possibility. The idea is unsettling not just because of its violence, but because of its inevitability once it begins. Unlike in the bigrip, where the acceleration rate might be gradual for most of cosmic history, phantom energy increases its dominance faster and faster. There's no slowing it down. The physics of it is self-reinforcing. Philosophically, phantom energy doom is a lesson in humility. It reminds us that the universe's current behavior, gentle, predictable acceleration, might just be a temporary phase. We have only a thin slice of observational history to work with, a mere 13.8 billion years of evidence in a cosmos that could last hundreds of trillions. For all we know, the gentle push of dark energy could be winding up for something far more aggressive. In a sense, this is the most cinematic ending imaginable, a countdown where every scale of structure is destroyed in sequence, ending with reality itself. It's the ultimate escalation, the opposite of a slow fade into darkness. The universe doesn't just die, it's actively dismantled from the largest scales to the smallest, leaving nothing behind but a question mark about what comes next. Most end-of-universe scenarios are defined by a certain finality, a catastrophic collapse, a runaway expansion, a quiet, endless cooling. But there's a subtler, more haunting vision, a universe that has gone almost completely dark, yet still produces the occasional flicker of light, as though it refuses to vanish entirely without one last gesture. That's the world of black dwarf supernovae, a future so far ahead that the numbers strain the limits of human comprehension. To get there, we have to begin with the black dwarfs themselves. These are not exotic objects born in violent explosions like neutron stars or black holes. They are the cold, dark corpses of stars like our sun. Stars that once shone for billions of years but have long since exhausted their nuclear fuel. When such a star dies, it sheds its outer layers into space, leaving behind a white dwarf, a dense, Earth-sized sphere made mostly of carbon and oxygen, glowing faintly with the leftover heat of its former life. White dwarfs do not generate energy through fusion. They shine only because they are hot. The last embers of stellar fire, over trillions of years they cool, fading from white to red to black. Eventually, their surfaces reach the temperature of the cosmic background radiation. At that point, they are effectively invisible against the dark backdrop of space. These are black dwarfs, frozen, inert, and for all practical purposes, dead. In most versions of heatdeath, that's the end of the story. Black dwarfs simply drift forever in the cosmic night, slowly evaporating via proton decay, if it exists, or remaining as cold monuments to a universe that once blazed with light. But there's a remarkable and relatively new twist to the story, suggested by astrophysicist Matt Kaplan in 2020. Under the right conditions, black dwarfs could eventually explode in supernovae, trillions of years after all other stars have died. The key lies in the slow, relentless force of quantum tunneling. In the cores of stars, nuclear fusion happens because the temperatures and pressures are high enough to overcome the repulsion between atomic nuclei. But quantum mechanics allows for a different route. Even in the absence of extreme heat, particles have a small probability of tunneling through the energy barrier and fusing anyway. In our universe today, this effect is negligible in cold matter. In a black dwarf, however, time is on tunneling's side, unimaginably long stretches of time, over spans of around 10 circumflex 100 years. Yes, that's a 1 followed by 1100 zeros. Enough quantum tunneling could occur inside a massive black dwarf to ignite runaway fusion in its core. When that happens, the black dwarf would flare into a thermonuclear explosion, essentially the same process that powers a Type Ia supernova today. For a brief moment, it would shine as brightly as an entire galaxy, outshining everything else in the universe. And then it would be gone, its matter scattered into the void as dust and radiation. The rarity of these events is staggering. By the time they begin, the universe will have been in darkness for incomprehensible lengths of time. Galaxies will be unrecognizable, their stars long dead, their black holes evaporated or on the verge of disappearing. The cosmic microwave background will have cooled to temperatures so close to absolute zero that even the notion of temperature loses meaning. In this desolate era, the explosion of a single black dwarf would be an event of almost unthinkable significance. The last fireworks in a night that has lasted longer than all of cosmic history combined. If proton decay is real, the black dwarfs themselves might not survive long enough for this to happen. They would crumble into radiation before tunneling could ignite them. But if protons are truly stable, then these distant supernovae could mark the final luminous events in the universe. After the last one fades, there will be no more light, ever. There's something uniquely poignant about this ending. Most apocalyptic visions are fast and decisive. The universe ends in fire or freezes forever. Here, the universe does freeze, but it refuses to be entirely still until every possible flicker of light has been wrung from it. It's not a single ending, but a series of final gestures stretched across unimaginable spans of time. For any hypothetical observers, and it's almost certain there would be none, these supernovae would be profoundly lonely spectacles. They would not herald the birth of new stars or the recycling of matter into life. They would be solitary bursts of brilliance in an otherwise absolute void, shining for days or weeks before fading forever into the cold. When the last black dwarf supernova explodes, the curtain falls for good. There will be no more stars to form, no more structures to collapse, no more matter to rearrange. The universe will enter a state of perfect, unchanging darkness. In that sense, the slow burn of black dwarf supernovae is not just a final chapter, it's the epilogue, the lingering note after the music has stopped, a reminder that even in endings the cosmos can still surprise us. The idea of vacuum decay, the possibility that our universe is sitting in a false vacuum, a temporary and unstable version of reality's lowest energy state, is already unsettling enough. In that scenario, a bubble of true vacuum could appear somewhere, expand at nearly the speed of light, and overwrite every particle, every force, every law of physics we know. Inside that bubble, the constants of nature might be entirely different, and the matter and structures of our universe might simply cease to exist. But things take on an even stranger dimension when you put vacuum decay inside the context of the multiverse. If eternal inflation is correct, our universe is just one bubble in an endless froth of bubble universes. Each bubble is its own self-contained reality, with its own properties, separated from all others by vast expanses of inflating space. We can't see or reach the other bubbles. The expansion between them is faster than light, but in principle they're out there. And that means vacuum decay is not just a single universe concern, it becomes a multiverse-wide phenomenon. In the eternal inflation framework, bubble universes form when regions of inflating space undergo reheating, cooling just enough for particles, forces, and matter to emerge. The energy state of the inflating space determines the laws of physics in each bubble. Most bubbles might be in a true vacuum, their lowest possible energy state, but some could be like ours, long-lived, stable-seeming, but actually metastable. If one such metastable bubble decays into a lower energy vacuum, the bubble of true vacuum that forms wouldn't just expand inside that universe. In principle, it could breach the wall between bubbles. The physics of eternal inflation suggests that bubble walls are regions where the energy state changes sharply, and if a bubble of lower energy vacuum reached that wall, it could tunnel through, seeding destruction in neighboring universes. Now, before the alarm bells ring, it's worth noting that in most versions of the theory, universes are so far apart in the inflating space that contact is effectively impossible. The walls between bubbles are not like the membranes of soap bubbles, thin and fragile. They're vast high-energy boundaries that expand away from each other at enormous rates. But impossible in cosmology often just means very, very unlikely, and given infinite time, unlikely things will happen. If such contact did occur, the result would depend on the relative energies of the two universes. If our bubble were invaded by a lower energy vacuum, the consequences would be instant and absolute. The advancing bubble wall would rewrite physics as it passed, changing the masses of particles, the strengths of forces, and perhaps even the number of dimensions. Everything bound by our current physics, from atoms to galaxies, would be obliterated in a fraction of a second. The flip side is that we could be the invaders in theory. If the true vacuum inside our universe had a lower energy than that of a neighboring bubble, a collision could seed our physics inside theirs. That collision would release tremendous energy along the impact boundary, possibly creating entirely new structures, or, more likely, annihilating anything that existed there. Cosmologists have speculated that if bubble collisions happen, they might leave observable scars in the cosmic microwave background, faint circular patterns where the collision altered the temperature distribution. Searchers for such patterns have so far come up empty, but our view of the universe is limited to what light has had time to reach us since the Big Bang. If a collision happened beyond our visible horizon, we wouldn't know. In the multiverse framework, false vacuum collapse is both more likely and less threatening to the multiverse as a whole. More likely, because with an infinite number of universes, some will inevitably be metastable and decay. Less threatening, because even if billions of universes are erased, an infinite multiverse still contains infinitely many others. The destruction of our bubble, while absolute to us, would be irrelevant in the grander scheme. There's something deeply humbling in that. We tend to imagine the end of our universe as the end of everything. In the multiverse view, it's more like a single snowflake melting while an infinite storm continues. The overall reality doesn't even notice. Philosophically, this takes the edge off and sharpens it again. On one hand, the end of our universe wouldn't mean the end of all existence. On the other hand, it makes our survival seem even smaller and more fragile. We are, perhaps, living in a long-lived but temporary fluctuation, a precarious balance that could be overturned without warning, either from within or from a neighbor we'll never see coming. And unlike the slow, predictable futures of heat death or proton decay, false vacuum collapse in the multiverse keeps the clock hidden. The event could happen tomorrow, or in 10 circumflex 500 years. The bubble wall could be unimaginably far away, or already on its way here, undetectable until it arrives. If it does happen, there's no final moment to witness, no spectacle in the sky. There is only this instant, and then the laws of nature change so completely that nothing recognizable remains. For us, it would be the end. For the multiverse, it would be Tuesday. The universe has no shortage of ways to end. Some are violent, tearing galaxies apart, collapsing all matter into a single point, or rewriting the laws of physics in a sudden quantum flash. Others are quiet, a slow dimming of the lights until nothing stirs, nothing shines, and nothing changes. Each scenario we've explored is shaped by the same two forces, what we know and what we don't. What we know tells us this: the cosmos is not static. It has evolved from a hot, dense beginning to the vast, structured expanse we see today. Expansion, gravity, entropy, and quantum effects are all in motion, and none of them stop. Every star that burns is a clock ticking down. Every galaxy drifting away from another is part of a story moving towards some kind of conclusion. What we don't know is the heart of the mystery. We don't know the true nature of dark energy, or whether protons decay, or if the vacuum state we live in is truly stable. We don't know if the universe is alone, or just one bubble in an infinite froth of others. We don't know if the end is an irreversible erasure, or a passage into another beginning. The scenarios we've walked through are more than just scientific possibilities. They're different philosophies of impermanence. The heatdeath envisions a universe that drifts into silence and stays there forever. The bigrip imagines a sudden and absolute tearing apart of everything. The big crunch and big bounce offer the poetic symmetry of endings that lead into beginnings. Vacuum decay shows us how fragile the rules we take for granted might be. Eternal inflation and the cyclic multiverse remind us that even if our universe ends, reality may have no end at all. On human timescales, these endings are abstractions, vast, cold mathematics, playing out over billions or trillions or Google years. They will not touch us, our descendants, or any trace of our civilization. But that doesn't make them irrelevant. Thinking about the universe's fate forces us to confront the limits of permanence. It makes us understand that the stars we see tonight, the galaxies in the telescope images, the atoms in our bodies, all of them are temporary arrangements of energy and matter. And yet, there's a strange comfort in that. The same physics that will one day erase all structure is the physics that allowed structure to exist in the first place. The end is not a betrayal of the beginning. It's part of the same story. Without change, there would be no stars, no planets, no life, no moments like this one. In the final accounting, whether the universe ends in fire, ice, silence, or transformation, the fact remains, it is here now, it is unfolding. And we, tiny, brief, impossibly lucky, are here to witness a fraction of its journey. The rest will happen without us, but we are part of it all the same. Perhaps the truest ending is not in some far-off epoch, but in our understanding. The universe will do what it will do. The question is what we choose to do, knowing that everything is fleeting, and that fleeting things can still be beautiful.